Now I'm going to read Chapter 12, Weather Forecasting. Producing a weather forecast. There are 6 steps to forecasting. 1 is collecting and assimilating weather data at the global scale. So all the weather data from around the world. 2 is quality check the collected data. So you want to make sure that the data is logical to the region it originates. For example, summer in Florida should not have snow. That's very unlikely. So if you have data that says that it snowed in Florida, you should double check that. 3 is define the maps, which we'll get to the maps later in the slides, but there are maps of different altitudes. Each map tells us something different about the atmosphere and the storm itself and the weather conditions. Also, the reason you need data at a global scale is because a lot of storms travel from one side of the world to the other. We see a lot of weather factors that are impacting the entire globe or an entire region. And so weather isn't isolated to one focused spot. It's influenced by things all over the place. And you need all of that data together to create an accurate prediction of what the weather is going to do. Step 4 is to begin the predictive/forecast phase, which is basically preparing for all the different things you'll need to do to predict it, which will be presenting the data. If you're on TV, you'll need to prepare the studio, you'll need to prepare yourself, you'll need to have everything in order, all the different components to present the forecast to the public. The 5th step is to prepare the forecast maps. Make sure that they are all ready. And step 6 is to present the forecast maps. So this is when you're really ready. You've done all the other steps, and you're about to predict the weather and present it to the public. Producing a weather forecast overview. So on the slide, there's a chart with different organizations that either collect data or present data. And at the top of that chart is the National Oceanic and Atmospheric Administration. That's NOAA. And they are the head of everything else. They are in charge. They are the ones that everyone else answers to for weather data. There are 3 branches under NOAA. The first one is National Weather Service, NWS. The second one is National Environmental Satellite Data and Information Service, NESTIS. I think that's how it's pronounced. I've never heard that one before. And the third branch says others. So that's other organizations that are involved with presenting weather data. Then the National Weather Service has branches underneath it. The National Centers for Environmental Prediction, NCEP, regional offices, so that's individual offices in different states and areas, and then others. I'm not sure what those are, but probably in the same vein of organizations that collect weather data, present weather data. And then the National Centers for Environmental Prediction have the Climate Prediction Center, CPC, the Environmental Modeling Center, EMC, the Weather Prediction Center, WPC, the National Hurricane Center, NHC, Storm Prediction Center, SPC, and others. And these are organizations that present the data. So the branches higher up, they collect the data, they analyze the data, they decide what needs to be presented to the public, and this last layer is what is where it actually gets out to people. Regional offices have forecast offices and centers. There are 122 weather forecast offices and river forecast centers. The book says that the weather forecast offices are where they produce local and regional weather forecasts, and forecasters at each WFO, Weather Forecast Office, tweak the computer-generated forecasts by using traditional forecasting techniques and knowledge of their particular forecast area to create a more accurate weather prediction. Acquiring weather data. Surface observations. So, surface observations are made by the World Meteorological Organization and weather forecasting offices. On the slide here, one is a buoy which collects weather data in the water. One is a NOAA ship, and one is a NWS forecast office. So these next couple pictures are actually similar to what we covered in one of the earlier chapters. I think chapter 1 or chapter 2, where we have the ASOS data center, data collection, which has a wind tower, all kinds of different sensors, and basically this data collection center helps gather all of the data for the temperature, the rain, atmosphere, that will then get used to predict the weather later on. The second picture has a weather balloon which is released into the air at least twice a day, if I remember correctly. It doesn't say on the slide, but if I remember in my homework, I'm going to double check that real quick. Yeah, they are typically launched twice a day. So the next slide is acquiring weather data observations aloft. So again, the weather balloon. Yeah, it says weather balloons are launched twice daily at midnight and noon GMT. That is, that's Greenwich Mean Time. And a weather balloon is also called a radiosonde. And it has 3 components. It has the parachute, which is attached to the instrument package. The instrument package is the part that collects all the data, and then the weather balloon itself, which takes the instrument package up into the air and collects the weather data from the atmosphere. And it's important to wear gloves when you handle a weather balloon, because the oils from our skin affect the balloon's ability to stay intact. It'll both affect the weather data and it'll pop the balloon when it gets to a certain height. Because the fewer particles are on it, the better. Weather maps, depictions of the atmosphere. So the weather maps vary by height, and the lowest one is the 850 map. Then it's 700, 500, and 300. And these are the upper air maps. .850 millibar maps are 1,500 kilometers, or 1 mile above the surface, and they can help forecasters with precipitation types. And they're away from the surface, so it does not experience as much daily temperature change. On .850 maps you can see moisture and warm cold air advection. So on an .850 map you will see advection. So on the .850 millibar map slide about advection, it has 2 pictures. You can see the isotherms, which is cold air advection coming down, and warm air getting pushed upward, like you see in a cold front. And the second picture has an actual loaf marker, and you can see again the isotherms from the cold front and the cold air advection and warm air. Also for .850, looking at the book here, not the slides, it says the solid lines are height contours spaced at 30-meter intervals, and the dashed lines are isotherms in degrees Celsius. Regions where the relative humidity is greater than 70% are depicted in shades of green. Areas of warm and cold air advection are showed with colored arrows. The next slide is about moisture. So here you can see the moisture in the air. The .850 map gives you one way of identifying the low pressure, based on moisture, precipitation, and advection. The 700 maps are 3 kilometers or 2 miles above the surface. And here is where you see winds, and winds are used to predict movement of thunderstorms. When air temperatures are 14 degrees Celsius or 57 degrees Fahrenheit or higher, at that level, the thunderstorms will not develop. And it is warm above high pressures, because if you remember, a high pressure on the surface is low aloft, and a low pressure at the surface is high aloft. So the 700 maps are the maps that show the air aloft with the warm low pressure above the high surface pressure. About the 700 millibar charts from the book, not the slides, it says the 700 millibar flow, which occurs about 3 kilometers above sea level, serves as the steering mechanism for ordinary thunderstorms that tend to occur in the warm summer months. Thus, winds at this level are used to predict the movement of these storms. A generally accepted rule of thumb used with 700 millibar maps is that when air temperatures are 14 degrees Celsius or 57 degrees Fahrenheit or higher at that level, thunderstorms will not develop. A warm 700 millibar layer acts as a lid that inhibits the upward movement of warm, moist surface air that might otherwise rise to generate towering cumulonimbus clouds. The warm conditions aloft are usually caused by general subsidence associated with a strong high-pressure center. So again, that's that pressure aloft is the opposite of the pressure at the surface. So if you are seeing warm air, that's the low pressure aloft, where the high pressure is at the surface. The 500 maps are 5,000 meters or 18,000 feet above the surface. They show the movement of the mid-latitude cyclone, which travels with the airflow. You can see troughs and ridges, which the troughs are low pressures and the ridges are high pressures. The high pressures are clear, dry weather. So 500 millibar maps are where you will see troughs and ridges. Troughs being the low pressures and ridges being the high pressures with clear, dry weather. Upper air maps and forecasting. Here we have a picture with isobars that show a trough and a ridge. The trough is a tightly compacted line going, in this example, it's coming down in this wave pattern. And the ridge, it's curving more upward like a mountain slope, but the bars are spaced out farther apart. So in this picture, the trough lines are closer together, and the ridge lines are farther apart. 300 and 200 millibar maps. So the 300 and 200 maps are near the top of the troposphere. This is where you see the winds and the jet stream. So once you have all of these maps, you put it all together. You analyze all the data, figure out what all this information is telling you about the storm. But basically, once you have all of the information you need, you compare the data and decide, is this storm going to strengthen? Is it going to weaken? What ingredients does it have to move or to grow or to weaken and go away? The slide for modern weather forecasting has 3 pictures of maps, 3 examples, which I won't get into. Satellites in forecasting. There are 3 main satellites used for forecasting. They are TIROS, it's spelled TIROS, TIROS 1, polar orbiting, and geostationary. Those are the 3 types of satellites. Polar orbiting satellites rotate north to south. Geostationary satellites go west and east around the Earth. So that kind of makes sense with their name. So polar orbiting orbits around the poles, and geostationary goes around west to east, the longitudes. It doesn't say anything here about the TIROS 1, but that might come up in a future slide. So let's see. Satellites in forecasting. So the geostationary operational environmental satellites, or GOES, provide visible, infrared, and water vapor images. And that's one of those geostationary satellites that go west to east around the Earth. Satellites in forecasting. Visible imagery is only available during the day, but it has higher resolution. Also, it does not really show temperature of clouds. Infrared imagery is available at day and night. It shows the temperatures of cloud tops. Higher clouds are white and usually cooler, whereas lower clouds are gray and are warmer. Qualitative versus quantitative forecasts. A qualitative forecast is observable but hard to measure and easy for the public, which basically means that it's presenting it in an easily consumable, more visual way rather than analytical, rather than precise measurements. But it isn't extremely technical. It's plain language and simple and easy for people to understand, even if they don't have the scientific background in meteorology. They can still understand what's going on. A quantitative forecast is measurable weather data. It's analytical, it's technical, it has the actual measurements, and it's more difficult if you don't have the background in meteorology and analyzing the data and doing the math and all of those very technical things. So again, qualitative is easy for the public, consumable, understandable in a simple way. And quantitative is not as simple, but it's more precise. It's more measurable. Types of forecasts. This has a couple maps on it, but I don't remember what these maps represent, so I'm going to skip this. Types of forecasts. The three types of forecasts are short-range forecasts, which are up to 48 hours in the future and have good accuracy. Medium-range forecasts, which are between 3 to 7 days in the future and have medium accuracy. And long-range forecasts, which are beyond 7 days in the future and have low accuracy. Because it's harder to predict what a storm is going to do the further out, the longer in the future. Another type of long-range forecasts are the 30 to 90 day outlooks. So those are going to be much less accurate than a same-day forecast. Watches and warnings. Here we have a couple maps. Showing a heat watch, a heat warning, winter watches, winter warnings. Just a minute, I lost my slide here. Very similar to what you see with a tornado watch or a hurricane watch and warning. It doesn't say exactly how those are determined. So I'm going to move on from this slide, but there are different maps that show watches and warnings for different types of weather events. And that is one form of forecasting. Thermodynamic diagrams. The figure in this picture is a typical display of an upper air sounding by a radio sonde. It basically has two lines coming up. One is temperature and one is dew point. And you will need to look at it to see how it's formatted and how it works. But this is called a skew-T diagram, and this helps meteorologists see the temperature and dew point vertically in the atmosphere. And one of the things you will see in this picture is that the temperature and dew point come up the chart separately, but they meet at some point and are merged together for a while, and then they separate again. And the reason why that's important is because when the temperature and the dew point are the same, that's when you have precipitation. That's when you have your clouds. And so this gives you a visual representation of when temperature and dew point are together, when they are the same. Thermodynamic diagrams part 2, because there are 2 slides to this. The figure on the right is also a skew-T. Skew-Ts are useful for assessing the potential for instability that can lead to deep atmospheric convection. The yellow area between the temperature and dew point represents the amount of energy available for a storm. Larger areas can mean stronger storms. So another thing that a skew-T map can have is it can show potential energy that supports a storm. And our final slide is forecast accuracy. So here we have a chart with local TV meteorologists on one line, the Weather Channel on one line, the National Weather Service on one line, and a baseline of perfection. That's basically exactly how the weather is. And this is a chart for the accuracy of 3 weather forecasting services. So the National Weather Service starts out very close to that perfect line, that ideal prediction of what actually happens. And then at some point it starts to waver a little. It starts to not be so accurate. And it kind of, but it is fairly close, but you can see the further out it goes, the less accurate it is. The Weather Channel starts out a little farther from the perfect line, but then gets closer as the chart goes up. So, and the graph is also showing on one line the predicted probability of rain versus the actual observed frequency of rain. So, for visual reference, when you look at it, you will see if the forecasting service line is above the line of perfect, that means that they over predicted the rain. And if the chart line is below the perfect line, it means they under predicted the rain. But generally, the National Weather Service was fairly accurate. The National Weather Channel had some trouble in the beginning, but became more accurate as time went on. The local TV meteorologist was much more inaccurate. They predicted much more rain than the actual observed frequency of rain. So that chart shows what each of those weather forecasting services predicted for rainfall and how accurate they actually were. The National Weather Service is more accurate because they have localized state data. They have data centers in each state that tells them the weather in that region. Another thing, this is the last slide, but I wanted to mention a couple examples of qualitative versus quantitative data. Qualitative would be it's going to rain, there's heavy rain, etc. Where quantitative would be there's 3 feet of rain. So in qualitative, people just want to know that there will be rain. They want to know if there will be a lot of rain. They want to know if there's just a little drizzle of rain. But with quantitative data, that's when you want a precise number. It's not just, we had a lot of rain. It's, we had 10 inches of rain. Or 3 feet of rain. Or it's we had so many feet of rain. And with experience, you understand how much rain is a lot of rain. But the average person who might not have experience with rain measurements, water measurements, they might not just off the top of their head know how much rain is a lot of rain. So qualitative data would be just saying that there is rain. It's a lot. So that is all for the chapter 12 slides. I'm going to be working on chapter 13 soon. And then I'll try and do a review of some of the previous chapters, the early ones, so that you can refresh your memory for anything you might have forgotten in the last 12 weeks. So, yeah, thanks for listening.